Hello, everyone. We've got just a couple minutes here before we start the webinar. So we'll start right at 11. All right, we'll go ahead and get started. My name is Eric Miller with Applied Engineering. Today we're going to be looking at Inventor Nastran and just some basics on validating your designs within Inventor. So the first step is to understand, I guess, the capabilities and choose the right tool. Obviously, there's a lot of tools out there that can assist with the FEA and validating designs. If you're using Inventor, obviously there's a couple built in. Inventor Nastran is one of them now that comes with the product design collection. And then there's also Inventor Simulation, which the stress analysis portion of Inventor. So the downside of Inventor Simulation is that it only does linear analysis, where Inventor Nastran can do both. So I guess the main reason you might want to choose the stress analysis, which is kind of the older, they still have it available in Inventor, is if you're going to kind of blend over to that dynamic side. So there's a dynamic simulation portion of Inventor which can kind of pull in the stress analysis, and do some, go through some motions and things like that. So they kind of work together a little bit better. But if you're doing any kind of, I guess what it shows here on the screen is, pay attention, ATTN, assemblies, time, temperature, or if it's nonlinear, then choosing Inventor Nastran is the best tool within Inventor. Obviously, there's a lot of other products out there. ANSYS is still a very popular, one of the leaders in FEA. So depending on the level you need to get to, I think those tools are obviously much more expensive. So nice to have a tool built into Inventor like Nastran, and it's a good solver. It's kind of a well-renowned solver. I think it developed by NASA a long time ago, and Autodesk purchased it at one point. So I think the capabilities are great there. Obviously, the nice part of it is you can kind of go back and forth between your Inventor model, run an analysis. You see something that maybe needs to be tweaked, go back. You don't have to leave the system or copy the file or create a dummy solid from it or something like that. We can go right back and forth within the same environment and make those changes to the model and then run the analysis again. So just a little bit of background here. Obviously, if you've done some FEA, you probably know this already. It's always good to kind of think about the FEA. You can get bad results, obviously, if you don't do things properly. So I think over time you kind of learn sort of some of the nuances, and obviously we've got some training that we can offer too on Nastran if you're interested in kind of going to the next level. But the tool isn't too bad to get familiar with. I think the key there is to understand if you are an engineer, you've kind of probably went through some of the classes and learn the theory, behind stuff. And I know the more you get away from college, the more it's, some of those equations might not be so fresh in your mind. But I think still just using your intuition and doing some of the preliminary work there is good. You want to kind of understand what you expect to see when you do an analysis, not just go into it blind. So think about some of those things. Like I said, FEA is just another tool to help us better understand our product and make informed decisions. So we don't want to just rely on it without actually thinking of, okay, does this make sense? The results we're getting is the high stress in the appropriate area that we would expect, things like that. So if you see anything weird there, there's a chance that maybe there's a constraint in the wrong spot, or maybe your assembly didn't have the appropriate contacts created and things like that. So there's the setup of the model is important in order to get correct results. All right, so just a little bit on whether we need to do linear or nonlinear. Obviously, the amount of deflection is a big indicator. If it's large deflection, then we probably got to do nonlinear. Obviously, if it's in the straight portion of the stress strain curve, then we know it's linear. That's kind of the difference between the two. But also the type of material. So is it steel? Is it a linear material, or is it plastic, rubber? Things that might be a little more non-linear and behave differently. So obviously in that case, then if we do have some strain stiffening, things like that, where our stress strain curve is there's no real linear portion of that. At that point, temperatures involved, things like that, we need to get into a nonlinear analysis. So again, kind of like I mentioned, it's good to kind of understand your model and what you expect to see out of it. If you're at kind of the, I guess some of the reasons you might be doing analysis is maybe before you release a design, you want to make sure it's going to be strong enough or not, not fail. So, before you even have a physical prototype, this is a way to test, as if it were a physical prototype. So, try to think about what the goals are, quantify your inputs. So that'd be your, what type of load is going to be applied to this? Is it on the appropriate surfaces? Make sure there's no kind of point loads where it could, cause some singularities in your model where there's a super high stress that you just can't get it to converge. Are there, what are the boundaries, boundary conditions and things like that? What are the constraints? So we build those things in. We wanted to make sure our materials, the appropriate, got the right yield strength, and it's set up properly so that basically the properties that go into our material is really what driving the math in this. So we can change materials and see different results. Obviously so that's important to make sure the right material is applied. Prediction theories. So what do we expect to happen if it's going to fail, if it's going to yield, if it's just going to bend a little bit but then go back, if it's in a linear section of the stress strain curve, is it going to fracture, things like that. So buckle. So then also just creating a free body diagram. Do some of this on your own. It's sometimes it can be kind of, if you haven't done it for a while, it's like, okay, you got to open up the old book again. But it's not a bad idea to try to get back in and understand just the basics there. All right, so the stress analysis workflow that we typically go through is shown here. So first step is creating the idealization. So that's really involves, okay, what type of element are we going to use? Make sure our material is set up properly. And by elements, typically there are three types. We have our line elements, which is kind of the simplest line or beam elements, you might call them. Shell elements is more of a surface. And then we've got the solid elements, where if you've got castings where there's different curvature, you've got multiple different thicknesses throughout. Typically, I guess from the types of products that I work on, typically the solid element is the most common. But if you're doing a lot of sheet metal stuff, then shell can be even a more accurate way to run an analysis. So keep those in mind. Then we set up, so we do our idealizations, and if it's an assembly, you can have, you might have some solids, you might have some shells in there. You can have those work together in the same analysis. And we set up our boundary conditions as step 2. So constraints and loads are the main thing there. We're just going to identify, okay, obviously you can't have, if you do have movement, in your model, we can do that, but we may need to then look at a different type of analysis to run. So whether it be kind of movement over time, or if it's got some you know, maybe you're looking at natural frequencies or modal frequencies, things like that we want to analyze and make sure that it's, you know, as a model goes through a specific, you know, cycle, where are the max loads and things like that. All right, so step 3 then is to run the simulation and analyze it. So once we have our, you know, the appropriate setup, and I guess one thing I kind of missed in there, the boundary conditions, is sort of the meshing. So that's kind of, I guess, built into running. You know, we do mesh it. We want our mesh to be, you know, it's kind of one of those, again, the more you do it, the more you kind of understand how many elements we need in order to get a good result. If you've got thin, you know, portions of your model where the thickness isn't really a lot there, you kind of want to take a look at that and make sure there's enough, you know, elements across the width of a part to be able to truly, you know, get the stress to have that kind of transfer from one side to the other. If you only have one element across the thickness, a lot of times you're going to see some, you know, some probably not great results with that. So just one of those things, we kind of take a look at the mesh, we can analyze that, and then eventually we want our results to converge. So we might have to refine that mesh and get to that point. So that's kind of where optimization, number 4, you know, after analyzing it, we see maybe a higher stress in one spot. So whether optimization is just refining the mesh to make sure we have a good result, but then also how do we modify our model in order to get the right results we're looking for and make sure that we're not going to fail. So maybe we're changing, maybe we're adding some material, maybe we're, you know, adding a stiffener, things like that, and then rerun our analysis. So again, if you are interested, I'm going to get into the actual tool here in a second, but if you are interested in class, we've got one coming up next week. So feel free to reach out to me there. My name's Eric with Applied, and we can get you signed up for it. So email her at go-applied.com. All right, let's jump into and just do a quick little run through of Inventor within Nastran, or sorry, yeah, I guess Nastran within Inventor. So first thing we'll do is just pop open a model, okay? I'm gonna grab this one. This is one of the ones we use in our class. Excuse me. And the idea is we're gonna, you know, have a specific task for this particular model. Obviously, you're designing it for a reason, right? So this one we're gonna bring in, and this is, you can tell there's a lot of different thicknesses here. So right off the bat, you know, we're looking at this model. We've got a few holes here, so you know, maybe that's gonna, you know, change how stress might flow through this arm, you know, and a fairly long arm over on this side, or I guess arm, leg, whatever you want to call it. But basically, it's rotating about this center piece here. So maybe it's some kind of linkage where we're gonna have a force, you know, on the top of this thing, or maybe at any of these holes in the center, and then another, you know, force, or maybe it's a pinned connection over here. So we've got to decide, okay, is this going to be strong enough? You know, you can look at, you know, it looks like they put nice fillets, you know, throughout. So that's a nice way to spread out forces. But obviously that, you know, we can try to simplify the model at times too. So sometimes fillets, obviously you get a few more mesh elements, and, you know, we want to make sure we don't see any, you know, sharp corners potentially. And if there is, you know, we have to understand, like even right here, you know, this is a fairly sharp corner coming. So, you know, maybe there will be a stress singularity at that point if the, you know, hard to mesh sometimes across small surfaces like that. Anyway, just things to think about, and obviously you want to look for symmetry sometimes. So in this part, you know, if we've got symmetry in this case, I'm looking at this top, maybe this is actually taking the top view, but left to right here, you can see it's fairly symmetric, right? So we could potentially, if we want to reduce the number of elements, we could cut that in half and add symmetry constraint to that, so that we only have to analyze half of it and understand that, you know, we maybe cut our force in half there as well, but then be able to get pretty good results. So, you know, sometimes it's nice to reduce elements like that. Sometimes it's nice to see the full model. So it just kind of depends on the situation and maybe how long it takes to run. Sometimes cutting the amount of elements in half can make it run, you know, much quicker. So definitely something to consider there. All right. So, you know, and obviously if we're thinking about, okay, you know, if this is a preliminary part where we haven't actually built it yet, we're doing some more, you know, kind of theoretical. We want to figure out, make sure it's not going to fail before we build one of these things. Or a lot of times what happens too is out in the field, we design this part, maybe it passed our initial test, but out in the field, it's actually failing. And for instance, maybe it's cracking, maybe it's more of a, fatigue situation where the initial stress of the load is fine, but over time there's enough wear and tear where we have cracks, throughout. So that's a different type of analysis. Or maybe there's, in this case, I wouldn't think there'd be buckling, but you can see that with the holes in here, maybe if there's a force acting down, maybe these arms buckle. So it depends on the type of, we do have to kind of, understand, I guess, if there is a failure in the field, what caused it, and then try to figure out how can we make sure we avoid that going forward. So that's another, very common type of, situation where you get some feedback from a customer or from the field, and you want to make sure, or just from prototype testing, and you want to make sure you get that resolved before it gets out to the masses. Or if there is a failure out in the field, we got to make sure we get the right parts to our service people, so we can go out and make sure the customer's happy and get that fixed ASAP. So a couple of different things to think about as you're going through that. So let's go ahead and take a look at how to get into the Nastran environment if you haven't done that. So it is an add-in within Inventor. So if you haven't installed it yet, it's a separate download. It comes with the collection, but you install it separately after Inventor's installed. And then what happens is it puts a little button right in here, an icon for the Inventor Nastran environment. So as far as licensing goes, nowadays it's kind of everything's moving towards subscription. So if you have a collection subscription, then you'd have access to this. So it doesn't necessarily have to go find a network license. In our case, we do still have some network licenses that we're using here for demos. So mine will go out and just kind of grab a license from our network. But if I click on that Nastran environment, then it's going to verify that and then jump into the environment. Okay, so here we are. One thing I guess I kind of forgot to do was check the material. Okay, so and actually right on the top, we're still basically in, we're in Inventor still. We just see a bunch of different tools now within the Nastran environment. So I can still bounce back. There's all my model tab, but right now I have the Nastran environment active. But we can go up and just verify, okay, I forgot to check my material when I came in, but I can see that it's right now set to mild steel. So that's good. We could change the color of it or whatever, in the appearance, but we're not worried about the appearance of it right now. We just want to make sure the right material is applied. Another place to check that is over on the left now. We see there's a kind of analysis tree, just like we would have for our model tree. You can even go back to the model tree and see those different ones. But I'm looking at the Nastran model tree. Let me expand those elements so you can see. So we've got Nastran model tree. There's a Nastran output, which we'll see eventually when we run an analysis, and then a Nastran, the different file. Let's see, I think just a Nastran file output there. So within the Nastran model tree, this is the idealization stage. Remember, that was the first. Well, actually, even before that, what we want to do is make sure that we've got the right analysis chosen. So up on the top here right now, you can see it says linear static next to that. So if I go to edit on that, we can actually modify, and change. We've got all these different types of analysis to do. Now we run through quite a few of these in the class. I guess the one nice thing about Nastran is that we can do heat transfer. So analysis there. So that's another part of this. So we could choose, vibration, fatigue. We can do, check for natural frequencies. A drop test option, shock response, random response. We go through some of those in the class, but obviously some nonlinear stuff, time, direct transit response, lots of different options for types of analysis to do here. Okay, so we're going to keep it simple, obviously, for the sake of demonstrating this in a webinar, obviously. But there's some different options we can choose over here. We can, say, as far as if this was an assembly, that's what this option does here, is choose, okay, how close do parts have to be before it creates automatically a bonded contact? That's if we use, automatic contacts. But in this case, we just got one part, so no big deal. We hit OK. Oh, another thing to mention, within an assembly, when you build your constraints in Inventor, I don't know if it's necessarily a downside, but when you pull an assembly in, you still have to, determine where the constraints are between components, and you have to choose how they interact together. Sometimes you might put a constraint on the, within Inventor saying these two are mated, but can they, maybe they slide. There's some friction there. So we have to kind of assign some of that stuff when we bring an assembly, into the Nastran environment to make sure it behaves the way we want. All right, so we got the right material, we have the right analysis. Now we can kind of keep moving down. It's all kind of sort of goes top to bottom in the model tree, but then up on top in our toolbar, in the ribbon, it kind of goes left to right as far as the options you kind of choose as you get to, the point of running an analysis. All right, so we're going to check. This is our idealization. So by default, it actually chose solid. That's kind of the default to pick a solid, and you can see it's got steel. If we go in here and do an edit on that, maybe we want it to be a different color. This is the color that's shown here is basically what the mesh elements are, the lines of the mesh are going to be. We can also change the material. So nice thing is too, right away, we can go into, we don't have to go assign it back in the model. We can actually apply different materials right within the Nastran environment without actually affecting the main model. So let's say I want to try this as an aluminum part or something like that. We go in here, go into the library. We've got the Inventor library and the Autodesk material library. You can also load your own databases for different materials maybe that your company has. All right, so I'm going to try, let's go aluminum 6061. We'll hit OK on that, and notice all my properties here for that material just updated. So we've got our density, we've got our modulus of elasticity, we've got the yield stress, tensile, or I guess yield stress, tensile stress options, and you can actually create your own materials within here. Let's say you have a specific aluminum that your company uses and it's just a little bit different value. Well, you can give it a new name, add this material, and kind of create your own within the environment. So let's just go with the default here for aluminum 6061. We'll hit OK there, and now that's been applied to this model. Notice up on top it still says steel. So again, we're just trying this other material for this analysis. All right. So as we kind of keep moving down, we could eventually we're going to want to mesh the model, but I'm going to skip right through that. We're going to come back and take a look at the mesh. I want to put in my constraints and loads first. Now, in my mind, I like putting in constraints first, so I think these two really should almost be in a different order. But if you look up on top and move kind of left to right, it actually does constraints before loads. Nonetheless, here let's go ahead and say let's apply. Yeah, we'll just go rather when you hit constraint. This is a fairly open and general dialog box. So we really have the option to choose which degrees of freedom we're going to remain fixed and which ones we're going to let free. So you can have no translation, and there are some options here too. If I go fixed all and pick a surface, that means all the nodes in that surface cannot move. So you can see translation, you got T and the X, the Y and the Z, and then rotation and the X and the Y, Z. You can kind of create your own type of constraint for each of these. We're going to say, let's say this, just for the sake, I know this could probably spin in a typical linkage, but we'll say we're actually going to fix that right now. Just, there's other ways if we want to put rotation in there and stuff. We could say, well, we could allow rotation, in the, maybe we should do that. Let's allow rotation there, and we'll fix this one over here to see how that works. So let's allow rotation in the Z for that. So we're going to go over here and just uncheck rotation in the Z, so they can all kind of move in that direction. And if we hit the little preview, it shows my all these little arrows. So they kind of have the degrees of freedom in each direction. There's two little it's almost like a little cone in each direction, one for translation and one for rotation. All right, just to kind of talk a little bit more about this too, we've got structural, there is pin, there's frictionless, there's thermal, so we've got different types of constraints we can apply here. I'm gonna hit OK on that one. Let's go over here and say we're gonna fix, you can see there's two. We'll say these are gonna be more of a welded joint, and then we're going to have the force on the top there. Obviously, if we didn't fix these and you said there was rotation, you put a force here, it would allow it just to rotate, freely, and we wouldn't actually converge to a solution. So we got to do something with this one over here, and we could do a couple different ways, but let's just go constraint here. I had those selected, so constraint automatically drop those faces in. We'll just say we're going to fix all those, at least for maybe my preliminary check. Eventually we can maybe take away some degrees of freedom just to make sure it moves just like, and there are some other ways to do that too, using connectors. We talk about those in the class a little bit more. Connectors are kind of a way to simulate what an assembly mechanism would look like with just working on a specific part. So you don't have to bring in these other parts to kind of, you know, to show how it actually would work. You can use connectors to try to, you know, sort of make it simplified a little bit. All right, so we're gonna fix those surfaces over there. Now let's put our force. Our load is gonna be, so again, when I hit the load section, this is the load. We've got all different types of loads that we can apply: force, moment, distributed load, hydrostatic, you know, and even when you get into the temperature side, there's body temp, initial conditions, temperature, radiation, heat flux. We're just going to keep it simple right now and just go with a simple force acting, you know, towards the left here. So we're going to pick both those. Now, if I pick both of these and enter in, let's see what you can see our coordinate system there. We're going to go in the negative y direction. So you can see right here the green arrow pointing the y is to the right. So we do have to use the negative to make sure the force goes the other way. So let's go negative 1,000 newtons going in that direction. Now it's actually, since I picked two surfaces, it's going to apply 1,000 newtons to both of those. So in essence, you've got 2,000 newtons going that way. So the way to kind of, you know, without having to, okay, I got to divide that by 2. Another way to do that is just to hit this check box for total force. So then it's going to apply the total 1,000 across, you know, both of them as if they kind of were one surface almost. So that helps, you know, depending on the situation. Maybe you do want 1,000 on both of those, you know, but in this case, I want to make sure it's a total of 1,000 newtons acting in that direction. All right, let's notice over here, I changed the density a little bit of these. You can kind of, if you want more arrows, sometimes too many is, you know, then you can change the size. So that's just more of a visual thing on making sure you can see where that force is at. Same with our constraints down here, be able to see those. So go ahead and close that out. Next thing we want to do the mesh. Okay, so based on the overall box that the part will fit in, it kind of tries to do a mesh, you know, at a specific level here. So this is in millimeters, element size. So basically, if I want to refine this a little bit, you know, the best thing to do is kind of take, you know, maybe just do it the default, see what it looks like, and then we can refine it if necessary. There's a checkbox here for continuous meshing that helps around cylindrical surfaces like this. You can also do linear, parabolic, depending on how stiff you want your mesh to be. Sometimes linear is better for, you know, for a stiffer part, whereas parabolic allows a little more flexibility. We can go into, there's a bunch of different settings in here too for refinement ratio, you know, the minimum triangle size. So in a solid, obviously, this is creating a bunch, or with parabolic, it's creating kind of triangles with nodes on the sides in order to connect all these my little elements to each other. So let's go ahead and just generate this one and see what it looks like. And we can see that the type of mesh that it created, it didn't look too bad. You know, across, like I mentioned, across a thickness, we want to make sure we have a couple elements. There's not a ton there, but obviously you got, you know, the round, so there should be at least maybe a few elements across that thickness. I think we could probably, you know, take this up a notch. But again, if you start with the more coarse mesh, run the analysis, refine the mesh, run it again. If our results really don't change yet at all, or very little, then you can assume that maybe refining the mesh doesn't give you a whole lot of extra benefit. If it drastically changes as you refine the mesh, then you know that hey, something's going on here where you might have to check for singularities and things like that. Let's just take it down a little bit, down to 3, and then generate it again, just so you can kind of see the difference, going from 4.7 down to 3. Another thing to keep in mind is the number of nodes and the number of elements. So we had 6,700 elements when I was at 4.7. I changed it down to 3, and it went up to 19,922 elements. So it does, you know, a little bit of a change there in the element size drastically changes the number of elements, but maybe this has a little, you know, we maybe have a better chance of getting accurate results with a finer mesh like that. All right, we've got our mesh, we've got our constraints and our loads, we have the material, we're ready to run this thing. So let's go up on top here and hit the run. Now what's happening in my model tree now, it's going to swap over to my output screen. So that's one of the nice things about Nastran is it's not just kind of blindly in the background running things. You actually get kind of a readout here of what's happening. Not that it's obviously some of it's kind of gibberish where it might be difficult to really interpret, but if there is an error or anything like that, it'll show here, and you can scroll back up, and so if I hit OK, looks like it completed. but we can go back to that output and actually go back to, some of those results and see, what the code, what the equations are doing in the background, what the solver was doing in the background. Nonetheless, here we did get some results. Let's take a look at what happened. We've got a max stress right off the bat of 95.78 megapascals. We can take a look at displacement. See where our max displacement is. Obviously, we would expect it to be up on top here, and that's the case. Our force is up on that top one. With these bottom two, this one could rotate, but this bottom one was fixed over here, so even just rotating, you wouldn't think this would move really anywhere else. At least in this, in the bottom leg, it's all going to be on this top one. So 0.1678 is the and that's the amount of millimeters it's moving. So very minimal. But let's say we're not really sure what the if we haven't used aluminum that much, are we what is the max stress and all that kind of stuff. So if we go to safety factor, that's kind of a nice way to just kind of understand. And here we've got a safety factor. Our minimum safety factor is 3.973. So even though it shows really red there, red is usually bad, right? But all it is showing where the highest, sorry, in this case, the safety factor, the lowest safety factor, but the highest stress is right in that, that corner there, which we would kind of expect. I think that makes sense, where, the max stress would be. It's trying to hold this. We've got all the force. We've got kind of that moment arm between the force and that amount of length acting on it. So it makes sense that our stress would be kind of right here. It's trying to hold on to that and make sure it doesn't break. But as far as the safety factor goes, usually we're targeting at least a safety factor of 2, obviously maybe higher depending on the industry that you're in. In my experience, with ag and construction, we're probably usually higher than that just because, you can always add a little bit more weight to it. It doesn't always, but when you're in the, like say for instance, aerospace and things like that, you have to be as light as possible. So then you're trying to hit those safety factors, and anywhere you can remove material and still hit it, you're doing good. So obviously less material is usually the better in those cases. So anyway, safety factor of almost 4, I feel pretty comfortable with that. And at that point, maybe if I go back and say, can we take out some more material, maybe turn these holes into slots and still, not worry about cracking this if we're, at all concerned about the amount of weight or the amount of material. I think, the more we do, say like, 3D printing and parts like that, like this one, if it's, a small enough part, we could easily make that in a 3D printing instead of maybe doing a full cast for this, depending on the type of material. And obviously aluminum, maybe we'll use a composite or something like that instead. But, the more and more we're trying to understand, how the best design a part, use the least amount of material, but also obviously that's, good for, sustainability, the environment, all that stuff. Use as small amount of material as we can, but still get the end result and make sure our part does its job. So I guess, yeah, from there, we could go back in and like I said, make some changes in the, Inventor, come back and rerun the analysis, make sure we're still at a good safety factor. But I think, for the sake of time here, we are at a half hour. That's kind of what I was targeting for the webinar. So I'll just take a quick look. If there are any questions, feel free to put them in the GoToWebinar on the right side. There's an option to add a question if you'd like. And I'm not seeing any in there right now. So I'll maybe just give another few seconds there, but I'll pop up again my contact information. Again, we've got a class next week. If this is something you're starting to use in your company, I do recommend taking it. It's an essentials class. We do try to get into a little bit more than what's covered in the book. There's not a chapter in there on heat transfer, so I do try to fit that in at the end of the class if that's something you're dealing with. So we'll tackle that next week, and yeah, hope to see you in there if anybody's interested in joining. So, all right, with that, I don't see any questions. So thanks again for your time today, and have a good one. Thanks, bye.